We're going to talk today about hydrolysis reactions as well as what happens when we have a hydrolysis reaction involving a polyprotic acid. So what we're going to do is start off here with a problem, and we're going to work it through here. And we have an sodium hypochlorite solution, NaOCl, 1.2 molar, is made by dissolving some of this in water at 25 degrees Celsius or 298 K. They have given us our hydrolysis reaction. And so what happens is once that NaOCl, as we know, is dissolved in water, it's going to ionize into the sodium ion as well into the hypochlorite ion. Now the sodium ion does not affect pH because it is conjugate acid of the strong base. And that strong base being sodium hydroxide, one of our strong bases. So we're not going to be worried about this one, but this OCl will have a hydrolysis reaction. And this OCl, the hypochlorite ion, we've got it rewritten down here, is going to react with water, and water is going to act as the acid donating a hydrogen ion. Now it's going to donate that hydrogen ion to form HOCl plus the hydroxide ion. Now, the very important idea to keep in mind here is when we produce this hydroxide ion and we write our equilibrium constant expression for this reaction, we're going to write our equilibrium constant expression just like we always do, but it has to be written as a Kb expression. Now, the reason it's a Kb expression is because we're dealing with a solution that's going to be basic because we have a hydroxide. So obviously our equilibrium constant expression is going to be OCl1 minus, that's a 1 minus by the way, multiplied by, I'm sorry, let's erase that. I made a little mistake there. Let's do products, OH1 minus HOCl over reactants, which is the OCl1 minus. There we go. And there is our equilibrium constant expression for this reaction. Now, the next thing it's going to do is ask us to calculate the value of this equilibrium constant. So we're going to be calculating the value of Kb. Now, we are not given, well, we're given some things that we can work with respect to an ice table, but we have to look way up here at the top and we have something given to us, and we have a Ka value for HOCl. So if we know that we have our Ka value for HOCl and we need Kb, we're just going to use the expression Ka multiplied by Kb is equal to Kw. And we've talked about this before. This is at 25 degrees Celsius. So for Kw, we can use 1.0 times 10 to the negative 14th. And we're just going to solve this for Kb. So we have Kb is equal to 1.0 times 10 to the negative 14th, which is Kw, divided by the Ka value, which is 2.9 times 10 to the negative 8th in this case. And so we're just going to run that through our calculator, and I get a value of 3.45 times 10 to the negative 7th. Okay, so that's important. So now we have Kb. We just did a Kb calculation. Now it asks us to calculate the value of the OH concentration. We could also take it a step further and go to the pH, but in this case, this was an old released AP question, and they didn't ask us to calculate pH. They just want the value of the OH. So we're gonna ice table. So we'll go back to our original equation. And there's our original equation, and we're gonna run an ice table up this guy. And we're not going to worry about water. And so it did tell us that our OCl concentration was 1.2 molar. It's going to completely ionize into the sodium ion, which again doesn't affect pH, as well as the OCl1 minus. And then we're going to have 0 and 0 here. It's going to go to the right, so plus x minus x, 1.2 minus x, x, and x. And you know what's coming next. Of course, we're going to, let me scooch this down. Of course, we are going to set it equal to Kb, which we calculated the value up above, which is 3.45 times 10 to the negative 7th is equal to x squared over 1.2 minus x. And we're going to solve for x, assuming this is a small value and less than 5%. We can double check that at the end. And then run a calculation on that. And I ran that through and I get 6.43 times 10 to the negative 4th and that is X, and that also is equal to our hydroxide ion concentration. So because it's equal to the hydroxide concentration, that's all we were asked for is the value of the hydroxide ion concentration. Now we could, of course, negative log that and subtract from 14 to get our pH, but it wasn't asked for in this problem. So next thing we're going to do is we're going to talk about polyprotic acids. And then once we do that, we're going to talk about how to deal with a hydrolysis reaction that involves a polyprotic. So let's do that right now. Okay, and let's kind of scooch this stuff down. So first off, let's talk about what a polyprotic acid is. And a polyprotic acid is going to be an acid with more than one hydrogen ion that can be ionized. So more than one hydrogen ion. Now, a monoprotic acid would be something like hydrochloric acid, HCl, with only one. But a polyprotic, a good example, maybe let's do something like H2SO3. So we could have our first ionization on H2SO3, and it ionizes one hydrogen ion, and then we're going to have HSO3 1 minus ion produced as well. Now we're going to have a Ka value for this, and we're going to call it Ka1. We call it Ka1 because it's the first ionization, and this is 1.72 times 10 to the negative second. Now, we can then take this value, or we can take this remaining ion, and we can also ionize it. So let's ionize off the other. And we're going to have a Ka2 value. And it's going to be 6.4 times 10 to the negative 8. Now you notice that these two values are pretty drastically different. This first Ka value comes off, the hydrogen comes off a lot easier than the second Ka value. And if we did have a third Ka, let's say we have phosphoric acid, which is going to be an example we're going to use. Phosphoric acid is H3PO4. Now that would have three, we call it a triprotic acid or just a polyprotic acid. There's going to be three Ka values, Ka1, which is going to be the smallest, Ka2 a little bit larger, and Ka3. I'm sorry, I reversed those around. We'll say Ka1 is going to be the larger value, less negative. Okay. Okay, so let's look at a problem that actually involves this guy, but we're going to look at it from the hydrolysis standpoint. And here we go. So we're going to deal with Ka-Kb relationships as well as hydrolysis reactions like we talked about at the beginning, and polyprotics all in one problem, and here's a good problem for that. So TSP, trisodium phosphate. This, if you go into a hardware store, trisodium phosphate is sold, Na3PO4. In chemistry, we usually just call this sodium phosphate, but they market it as trisodium phosphate. It's a cleaner. It's used to clean walls, floors, really strong cleaner, especially before you paint a wall in your house. They might use trisodium phosphate to get any stains off, and then we could paint over. Okay, now that should be as typo warns. So the label on trisodium phosphate, when you go in there, warns that it's very caustic and alkaline. It's going to produce a basic solution. So the question is, what is the pH of a solution made by adding 45 grams of TSP, trisodium phosphate, to 1 liter of water? Okay, so we're going to do a bunch of different things here. So first off, let's convert our grams to moles, and then convert that to molarity. So we have 45 grams of sodium phosphate, and we're going to convert that to moles of sodium phosphate by dividing by the molar mass of sodium phosphate. 3 sodiums, 1 phosphorus, 4 oxygens. 163.91 is our molar mass. Divide those two and we get 0.275 moles. We're then going to convert that to molarity by dividing by 1 liter. Okay, it's the same. So we get 0.275 molar sodium phosphate. That's the solution that gets made. Now, what's going to happen, as hopefully you can recognize, is this sodium phosphate is going to ionize, and it does ionize. It's got a sodium, and it makes it really, really soluble into the sodium ion and the phosphate ion. Now, the sodium ion does not affect pH, but the phosphate ion does, because the phosphate ion is the conjugate base of a weak acid And the weak acid that it's the conjugate base of is HPO4 2 minus, or phosphoric acid, which is H3PO4. So what we're going to do is we take this phosphate and we're going to react it with water. And remember, it is a conjugate base. And so it is going to accept a hydrogen ion from the water to form HPO4 2 minus plus the OH ion. Now that OH there is going to obviously cause the solution to become basic, and that's what we're working on here, and that's what we're trying to calculate for the pH. So we're going to ice table this guy. Okay, so our starting molarity, as we found was 0.275 molar. And we're going to run this through. So reactions going to the right, plus X, X, 0.275 minus X, this is minus X as well, right? And so we're going to have a KB is equal to X squared over 0.275 minus X. Assume X is small, let's get rid of that. So what we need is KB, because it was not given in this problem. And they usually don't give us KB in these problems, but they do give us Ka. So down here we have three Ka values. We have the Ka value for H3PO4, we have the Ka value for H2PO41 minus, and we have the Ka for HPO4 2 minus. So this is the one we're going to use in this reaction, because that's what we're dealing with here. So we are going to use this Ka, but we need to convert it to Kb first. So we're going to use Ka multiplied by Kb equals Kw, assuming this reaction is at 25 degrees Celsius, 298 Kelvin. So that's going to be 1.0 times 10 to the negative 14th, which is Kw, divided by 4.8 times 10 to the negative 13th. And we basically just solve for Kb, and that's going to give us our value of 4.2, I'm sorry, 0.0238 is what I get, and that is going to be our Kb. Now we're going to take that value and we're going to plug it in here, 0.0238, and we're going to solve for X. So let's multiply 0.0238 by 0.275 and then take square root of it. And I get an X is equal to 0.0809. Okay, and now that is X, that is equal to my hydroxide ion concentration. Now, originally we were asked for pH, so let's just take the negative log of that. And negative log of that will give me POH, which is going to be 1.09. And then let's take pH is going to be equal to 14 minus 1.09 to get our pH. And so that's going to give me 12.9. And now, so pH of 12.9, as the warning label on the container says, it really does form a very basic solution that is going to be caustic. So, and that's what makes it such a good cleaner. So again, one of the things we have to remember is, if we're dealing with polyprotic acids, which one of the ions are we dealing with? In this case, we're dealing with Ka3. Sometimes you'll deal with Ka2, or just Ka1 with respect to a monoprotic acid in your hydrolysis equation.